Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at ThermoAnalytics and host of today's webinar. Our presenters today are Kamesh Kethireddy from ThermoAnalytics and Hannes Carlson and Karthikeyan Nanasundaram from Volvo Cars. Kamesh joined ThermoAnalytics in 2018 and is our Business Development Manager, where he helps formulate new business strategies and support customer relationships in Europe and Asia. He received his Master's of Science in Mechanical Engineering from RWTH Aachen University and his MBA from Gizma Business School. Kamesh worked with TAITherm and our team for over a decade prior to joining TAI as a loyal customer during his time at Audi and Volkswagen. Hannes is from Lund, Sweden. He graduated with a master's degree in mechanical engineering from Lund University, and he started at Volvo Cars trainee program in the climate department in 2017, where he continues to work today as an analysis CAE engineer. His current area of focus is on system simulations on different climate systems. Karthikeyan from India graduated with a master's degree in applied mechanics from Chalmers University of Technology in Gothenburg, Sweden. And upon completion of his master's thesis at Volvo Cars, he has since joined the climate CAE department there as a consultant earlier this year. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. And we are also recording this webinar, which we'll be sending you a link for the recording and the slides following this presentation. And with that, Kamesh, if you're ready, you may begin.
Yes, Chris, thanks for the introductions. First of all, I extend my warm welcome to two guest speakers today, Hannes and Karthikeyan from Volvo Cars, and they agreed my request and to show their work at our webinar. First, I will talk a little bit about the motivation about the cabin methods, what are the challenges associated with that, talking briefly about different modeling techniques, and later Hannes and Karthikeyan are going to talk about the exciting case study and the success story at the Volvo Cars. At the end, we can go through some of your Q&A. Market regulations of the carbon footprint legislations, the market demands and all these things are driving towards the electrification. The EVs, as all of us know, operate very well between 15 and 25 degrees ambient temperatures. The range can be going very much low if you go towards the strong winters and strong summers. One of the reasons is like the energy from the battery is used by HVAC system to make sure the guy inside the cabin is comfortable. The HVAC is one of the primary consumers of the energy, and sometimes it can take around 30% equivalent energy that you can use for range. Every watt of energy is very important, especially in EVs, since we don't have waste heat coming out of ICE engines. There is no luxury of heating the whole cabin. So how to make the passenger more comfortable quickly and with less energy usage? It's all the big questions. If you save 1 watt of energy in the cabin, you can use it for driving additional auxiliary devices, driving an extra mile, or driving to the next tank station, for example. But still, we cannot compromise on any of the aspects of the passenger comfort, and some things like also looking into time to comfort. These are all very important things to be taken care of. This led to the shift of focus from the conventional methods to more understanding the basics, trying to look into more human-centric designs, try to understand how a person sitting in the car reacts with its surroundings, with environmental conditions, a transient change of those conditions, the thermal inertias of the heavy components like seats, for example. Most important thing is to understand the physiology of the person, the change of the skin temperatures, change of the core body temperatures, the impact of the activity levels, like if the guy coming into the car, is he coming from an office comfortable climate situation, or is he sitting in the bus stop for 10 minutes in a cold climate? And those kind of situations should be taken care of. Is the guy is a passenger or driver? They have different MET levels, so that all should be taken care of. And what is the effect of clothing? This all sounds complicated to understand, but you need to take care of the physiology of a person and the comfort of a person into account to optimize the energy. Fortunately, this is all not a magic. There is a physics associated with this, and all those equations are implemented in the software, and the users can take advantage of that. And like I was telling, like the range is tremendously affected by the HVAC, which you use for like comfort calculations. So they are inversely proportional. So the challenge is what is the how to strike or how to find the balance between the comfort and range, how to size the systems, and what is you have to understand what is the performance of the materials on the roof or door panels or any other things inside it, and what is the effect of the glazing things, and the size of and the position of the resistors and things like that. Most importantly, trying to understand the active comfort devices. What is the impact of a neck warmer, heated steering wheel, or a ventilated seats or heated seats, or the radiant panels radiating the heat onto a person, or some kind of warm pads touching your knees or your elbows. These create a kind of local sensation and local comfort. Basically, the active comfort devices create a local environment, which create a kind of micro environment around a person and try to make him comfortable with less energy use. And even the putting the equivalent temperature around a person really at a relatively colder level. I think that is the most important thing to understand. How can I optimize the energy and make the guy comfortable with less usage of the energy, but still maintaining the equivalent temperature relatively colder? That is the core, and that's the name of this game. Finally, you need to adjust and enable and assess the comfort performance of various design variables. Try to understand what is the hardware cost related to that and what is operational costs, like heating up or cooling down of any of these things. And this is and also you have to understand what is the cost benefit analysis and what it brings. And the one way of looking into things is like physical tests. That seems to be pretty accurate, as you can see them, you can touch and you can feel them. But there are some challenges associated with that. First of all, you need to have a prototype. You have to bring the prototype to a measurement location. It could be anywhere in China, North America, or Mexico. And it has a challenges of the logistics and the cost associated with that, and also about the legislation. For example, even something, if everything is worked out, if you want to change any design variable, it is too late in the development process and often ends in over designing the product. That is exactly the reason why simulations are very useful and in fact mandatory to understand the design variables in every design phase. It could be in early design phase or in the later design phase, and to increase the performance of a product and also reduce the costs. I think this is one of our primary differentiator of TAITherm. You can use it in the early design phase to understand what if studies, understand, for example, the glazing of the glass on the dashboard, and try to understand the solar impact on the sensors on the A-pillar or under the dashboard or in front of firewall, and what is the performance of the insulation material around that, or like the positioning of the sensor, solar sensor, or what is the impact of solar load on the electronics in the rear view camera or anywhere. Those are the design variables you can quickly do. In the later phase of the development, you can even do high fidelity calculations, combining with 1D tools, combining with 3D tools to get the local convectional effects and things like that, include more physics, and even trying to do a kind of controller strategy based on human comfort, and try to do those kind of scenarios and understand right away. And there are some methods available. I'm going to talk a little bit here. Irrespective of what kind of fidelity you use, what kind of design phase you are in, TAITherm checks all the boxes for cabin methods and human calculations. It runs the transient calculations, running and modeling the temperature-dependent material properties, taking care of thermal inertias like for the seats or any other heavy components, trying to model the surface properties, glazing parameters, solar effect, solar loads, and things like that. And I already touched on most important physiology and comfort aspects. However, the main difference, if you see from top to bottom, the fidelity increases, but the TAITherm remains the same. But the most important difference is here how you model your fluid volume. In the first top two things, you split the whole cabin volume into few sub volumes, and everything is represented by one or more fluid nodes to represent the fluid. But if you come down, you can increase the fidelity of fluid volume. For example, here you use the Cool 3D from GT. I think Hannes is going to talk more about that. If you go down, you can even couple with the 3D CFD, where you can do flow separations and more complex convection analysis. You can use the steady state or pseudo transient or transient analysis, depending on what is your application. In the later, this is the full coupling of 1D, 3D, CFD flow, and complete thermal, including physiology of a person inside the cabin. This is a kind of a digital twin. You can get very accurate results with that, but of course it takes a little bit more time. And we have a new software, Rapid Flow, which lies between these two methods, but it is close. It's closely to CFD, but it's very fast compared to CFD. And the last one is the TAITherm mannequin coupling, where you see in the picture is a mannequin which has a lot of sensors, temperature, pressure, and humidity sensors. They are internally connected to a TAITherm software, and TAITherm will predict the comfort and the comfort of a person based on the change on the environmental conditions. With that, I will let our Volvo Cars guys to talk about our success story. And with that, I will give it to Hannes and Karthikeyan. Hannes, are you ready?
Yes, thank you, Kamesh. Yeah, so this presentation was initially a master thesis performed by Karthikeyan and Harikrishnan. Karthikeyan is here with me today to present, but Harikrishnan unfortunately couldn't attend. They studied at Chalmers University, where they did the thesis in cooperation with Volvo Cars. We would also like to say thank you to Gamma Technologies and ThermoAnalytics for their support during the thesis. Oops. So I'll start with some background and motivation for why we wanted to do this in the first place. So with a multi-zone cabin volume, you can predict the average cabin temperature quite well. So you can get a sense for the heating or cooling need of the cabin, but it is less accurate for predicting local temperatures and non-uniform flow fields. So the goal here was to investigate if a GT suite and TAITherm coupling could improve the predictability for such cases. So moving down here, and then couple this with system simulations. So that's why a standalone CFD is not really feasible in this case. The methodology is quite simple. So it's built through a co-simulation interface that involves GT Suite and TAITherm. So GT Suite will solve the fluid domain and calculate heat transfer coefficients and fluid temperature, and then communicate that to TAITherm that solves the wall temperature and then communicates back with GT Suite that specific typing tools. As a second step, a 3D CFD flow solution can be imposed instead of solving for the airflow directly in GT Suite. So that means that you get the HTC and the flow field from the CFD map, and then GT only calculates the fluid temperature, which it then would communicate to TAITherm. But that we will go more through later. And now I leave it to Karthikeyan to go through the results and the methodology that they used.
Thank you, Hannes. So this is Karthikeyan, and I'll be taking you through a bit about the modeling procedure and the results that we got. So this slide kind of explains the general workflow that we employed for this particular modeling process. The first step was to take the cabin geometry and do some pre-processing and meshing in ANSA. This we did this to make sure that the geometry was airtight and didn't have any leaks, and also to make sure that we meshed the geometry appropriately as required by the co-simulation model. And once we did that, we imported the geometry to TAITherm. And in TAITherm, we modeled the thermal structures of the cabin. And I'll talk a bit more detail about that. And we also had to import this model from ANSA into this interface called Cool3D, which is an interface within GT Suite, where we get to define the flow space and the blockages. So basically, the seats are the blockages, and once the flow domain is described, it is then kind of discretized in Cool3D by splitting the flow domain into these flow cubes, which is a kind of a very coarse way of discretizing the fluid domain. So these flow cubes were like 100 cubes. And once we had all these both the models ready, we had to import them into our system simulation interface in GT, where we get to define the boundary conditions and the co-simulation parameters. Okay, so basically, the purpose of using TAITherm is to model the thermal structures. And ideally, if we want to capture the heat transfer that's happening within the cabin and the ambient temperature and the ambient conditions, we would want to model the whole car, because every component or every layer within the car body will kind of contribute to the heat transfer in one way or the other. But the problem with using this whole complicated car model is that the geometry is a bit more complicated than a simple cabin model, and it would require a large number of mesh elements, which is not suitable for this co-simulation interface. So because of that, we had to find a simplified way of doing stuff, and that is why we took this cabin geometry, as you can see here, and we modeled it in such a way that it represents the car from a thermal point of view. So this cabin model kind of mimics the whole vehicle model in terms of capturing the heat transfers and the thermal structures. For example, if you take a component such as the door, a door might have more complex geometries and multiple layers, but in our cabin model, we only had one layer, one structure in the geometry. But in TAITherm, we had the feature of doing this multi-layer modeling. So basically what we do is we take a single material and then we define it as a multi-layer model. And here you can see we had defined it as a 5-layer model, being where basically this is one material and then there's an air gap, another material, another air gap, and another material, such that this one structure will represent the door and all the layers within the door. And also we had an option of in TAITherm we had the option of creating user-defined materials. So we had the privilege to use a bit of averaging of material properties to create our own user-defined materials, so that we can capture the thermal structures more accurately. So once we made all the models, we had to in order to validate our model, we had to do some simple tests. And we did this heat up test in our climate wind tunnel here at Volvo cars. So basically the test conditions are, we set the ambient temperature to -18 degrees. And then we set the vehicle speed, which is basically the speed of the wind in the wind tunnel, to 50 km/h. And then the HVAC conditions were only the floor vents were active and there was no recirculation. And we tried for 4 different blower settings. And we also had sensors at the inlet vents to measure the temperature and the mass flow rate of the air that is entering inside the cabin. And apart from that, we had sensors placed within the cabin volume. So this slide kind of explains how the sensors were placed inside the cabin. So basically 12 different zones were of interest to us, which is the head, chest, and the foot of the 4 different seats. So we placed sensors at these 12 different zones and then recorded the temperature throughout the test. And we placed the sensors in the same location in our model as well, so that we can compare individual zone temperatures as well. And we also kind of calculated the average of all these 12 sensors to kind of get the average cabin temperature. And once we did that and we compared the results with our model, so these are the curves that we got. So basically the red curve is the experimental curve. And these three curves, which are the HTCM 1, 15, and 20, are the curves that we get from our simulation. The HTCM basically stands for heat transfer coefficient multiplier. So what happens is that when you do this co-simulation, the heat transfer coefficient between the TAITherm model and the GT Suite model is not captured properly because of the way the geometry is discretized. And in order to kind of capture the heat transfer more accurately, we need to scale up this heat transfer coefficient by a factor of 15 or 20 to get it closer to the experiment. So this is the way of calibrating our model. And when you can see in this graph that when we use a heat transfer coefficient of around 20, our simulation curve was quite close to the experimental curve. But if you look at the individual temperature zones, like here we've shown you the driver head and driver foot position, even when you use a heat transfer coefficient multiplier of 20, in some places the simulation does not come close to the experiments. And this is one of the drawback of this method. And to kind of make up for this, we needed to go for the more advanced method, which is the 3D CFD mapping. So basically, in this method, apart from using this method is basically an extension of what we saw so far. So apart from modeling it in TAITherm and GT Suite, we also run a set of steady state simulations in a 3D CFD software. In our case, we use StarCCM. And then we kind of map the flow fields onto this co-simulation interface such that the fluid velocity and heat transfer coefficients are captured more accurately. And when we do this, there's no large increase in simulation time. We just needed some extra time to do these steady state simulations in the 3D CFD software. But so yeah, when we use this method, this is kind of the general workflow. So basically, this part is something that you've already seen so far. And what we do additionally here is that we do the StarCCM simulations, and we take the CFD data and we import it to the GTEs, which is the system simulation interface. And apart from that, we use the mesh data from StarCCM to kind of discretize our model in Cool3D. And when we do this, we can see that the experimental curve and the simulation curve match quite closely next to each other. And when we did this, we tried for 4 different blower settings. So which means we did 4 set of steady state simulations in StarCCM, and we mapped those CFD data into the co-simulation interface, and this is the results we get. And the advantage of this method is that when we looked at the individual temperatures, like driver head, passenger head, or the other head and foot positions, it was able to capture the temperatures quite accurately in all these localized zones as well. So you can see here, and these are the graphs that we get for the foot temperature at the 4 different positions. So with this method, we were able to get more accurate results. And I will give it to Hannes to talk a bit more about the pros and cons and a bit about the conclusions from our thesis.
Thank you. So the pros of the TAITherm and GT Suite co-simulation model is that it increases predictiveness as less calibration is needed, which we saw in the first part of the presentation. It also enables better evaluation of local temperatures. It enables better evaluation of non-uniform flow fields. For example, if you want to investigate higher circulation degrees or partial climatization. This is not something we've really, let's say, investigated in this thesis, but we think it's a fair assumption since you are imposing the flow field. It also enables the inclusion of comfort modeling via TAITherm, which is a nice bonus. For example, if you want to study the effects of radiative panels on the comfort, then you can't do that without comfort modeling. And via TAITherm, we also get more realistic sun load, which is a bonus then. The TAITherm and GT Suite co-simulation model in terms of drawbacks then is that it's computationally a bit heavier than the multi-volume cabin. It requires more manual work to set up the geometry, especially initially. It also requires 3D resources. So for example, if you're interested in a lot of different HVAC settings, then you need to run a lot of 3D CFD maps so that you can run it. It also comes with additional licensing costs since you need both TAITherm and GT Suite and also a co-simulation license. So to conclude, the TAITherm with the GT Suite flow solution was shown to, with calibration then, you can get a good match with the test data, but it struggled a bit with predicting local temperatures. CFD mapping, on the other hand, showed good comparison to test data, both for average and local temperatures. We did see some local temperature discrepancies, but I think that's to be expected considering the test uncertainties. Computationally, it's less expensive than a full 3D CFD run, but still gives fairly accurate results. It is more computationally heavy than a multi-volume cabin, but it's still fast enough for overnight runs. So maybe it's not suitable for all types of analysis, but certainly for some types of simulations that you want to do. So final remarks then is that the co-simulating GT Suite and TAITherm with the 3D CFD mapping is a great tool that enables more detailed and complex analysis of climate comfort attributes and energy efficiency, while still maintaining a reasonable computational time compared to a multi-volume cabin model when you couple it to system models. Thank you. That was
yeah. Thank you.
All right, thank you. Let's go ahead and get to the questions. First one here. Why is there a need for calibration when you don't use CFD mapping, and why isn't calibration necessary when you do CFD mapping?
Yeah. So yeah, basically, when you don't use CFD mapping, we have this flow domain discretized as these flow cubes, which are basically this 100 mm cubes. So because they are discretized in such a coarse way, the heat transfer coefficients are not captured properly. So because of that, we needed to do a calibration. But when you do a CFD mapping, the co-simulation kind of uses the mesh that was generated by the 3D CFD software. And since the discretization is more fine when we do the CFD mapping, the heat transfer coefficients are captured more accurately, and that eliminates the need for calibration. Does that answer your question?
Yes, thank you. Next question. Have you also applied solar loads to your model and test setup?
Yeah, I can answer this one. So no, we haven't done that yet. For this, I mean, since this was only a half a year thesis, we were, I mean, we had a bit of a time constraint, and also it's sometimes hard to get testing time. So we decided we wanted to start on like the, let's say, simpler case, which was without solar load. And then when we know that we get the physics right for that, then we can start to think about including radiation, for example. So that would be something we want to do now. But as a first step, we wanted to see if we could just capture the thermal aspects of the simulation. And then we want to add complexity on top of that rather than trying to model everything at once and validate.
Okay, thank you. Why is the time step used in the GT model lesser than that of the TAITherm model?
Yeah, I can get this. So basically, when the GT basically solves the fluid domain, so it tries to capture how the flow field is distributed within the cabin, and the fluid is a more dynamic process. So it's a very highly dynamic process. So in order to capture the fluid domain, you need small time steps because within the fluid flow, the kind of the flow field changes quite quickly. But when you take the TAITherm model, which captures the temperature and the energy distribution within the structures, that is not as highly dynamic as a fluid process. So for that, a large enough time step would sufficiently capture the physics quite accurately. So yeah, that is why we needed a smaller time step for the GT model.
Perfect, thank you. Next question, how long does it take to go through the complete process? Cabin setup to co-simulation setup to the simulation itself?
I mean, if you kind of have everything that you need to set up the simulation, namely the geometries and the coordinate positions of where the vents are located and how we're going to place the vents and everything, I think it's a matter of maybe a couple of days to kind of set up the whole thing. But if you are running the steady state simulations as well, you need to allow some time for that modeling and to get those results as well. But the whole process kind of takes a few days, maybe, if you have all the data. But if for us, for example, modeling the thermal part in TAITherm, it took us a bit of time because we had to do this multi-layer approach, and it was we had to kind of use our engineering judgment to do a bit of averaging. So that kind of took time. But if you have a simpler cabin with all the material properties are well defined, then I think it's only a matter of a few days to set up the whole thing.
Okay, thank you. Got one more. Why are we interested in modeling individual temperatures?
Yeah, I can answer that one. So there are a few different reasons for this. One is, of course, that if we manage to capture the individual temperatures, then we know that we can start to study different, let's say, control strategies where you maybe climatize only part of the cabin, or you have a high recirculation degree. So that's one part, and it also makes it a bit easier to, even without comfort modeling, you can start to judge a bit the comfort if you know what type of temperatures you have around the person. So if you only have like an average temperature, then it's a bit harder to correlate that to what a person would experience. So it makes that part easier as well. So those were the main reasons why we wanted to do it.
Okay, another one coming through here. Did you use the Berkeley model and TAITherm for comfort?
No, so in this thesis, we didn't actually study the comfort for the same reason that we didn't include the sun load, which was that we wanted to see if we could capture just the thermal parts of the cabin first. So here at Volvo Cars, we are actually doing a thesis now with TAITherm and comfort modeling, but I am not supervising that, so I don't have an answer for what type of model they use, unfortunately. But that would be like a next step for us to look at the comfort part. Now, for this thesis, the purpose was only to see if we could capture the thermal aspects of the cabin.
Okay, well, thank you, Hannes. That will do it for the questions. Actually, we got one more. What was the cell count of the CFD model used in your simulation?
CFD model, yeah. So basically, when we did the pre-processing or meshing in ANSA, we had the guidelines to use a mesh count of 20,000 to 30,000 mesh elements, because that is kind of the range at which the co-simulation works perfectly. But when we did the 3D CFD mapping, where we had to do the meshing for the 3D CFD software, which is like Star CCM, we didn't really have any kind of guidelines to go by, and it's more of just a kind of our engineering judgment. And if I'm not wrong, I think we used around like 2 million cells for the 3D CFD. But since it was a steady state simulation, it didn't really take a lot of time, even though we had quite a fine mesh with the 3D CFD software.
Okay, Looks like that'll do it for the questions. So thank you, everyone. That will complete today's webinar. We appreciate all of our attendees for attending today. You will all be receiving a follow-up email this afternoon containing links to download the presentation slides and watch the recorded webinar session. Again, thank you, everyone, and have a nice day.
Yep, thank you.
Thank you.
Thank you.